Tamane, and this is the Constant Velocity Lab for Physics 1. So this lab emphasizes the principle of Newton's second law, which is force is equal to mass times acceleration. There's some important information to know before continuing, which is Newton's first law, which is anything in motion will stay in motion until acted on by an external force. We of course have Newton's second law, which states that a force is equal to mass times acceleration. We have constant velocity, which is a constant speed in the same direction with no net force. We have the impulse momentum principle, which is a change in momentum is equal to a force applied over a period of time. And using these principles and laws, we were able to derive a few formulas. The first being the velocity update formula, which states that the final velocity is equal to the initial velocity plus F net over m, which is our acceleration, times a change in time. And the second formula we have is our position update formula, which states that the final velocity is equal to the initial velocity final position is equal to the initial position plus average velocity times time. Now, our system, which the experiment was conducted, was through a ping pong ball. So that was our system, and our surroundings was everything else, including the push force, the surface, gravity, and now the change was the ball was pushed at a constant velocity to the right. And using our experiment, we were able to find the initial velocity, which is calculated through the change in velocity is equal to the change in distance over a change in time, and we got that to be 0.4 meters per second. Now, the experiment was conducted, and an analysis software called Tracker was used. And Tracker was helpful in order to determine the time and the position of where the ball was at. A total of 12 data points were used, and this experiment was calibrated using a package in the back that was 0.22 meters, and this was used in order to help find our constant velocity. And this plot right here is the data values of our ping pong ball that's moving at a constant velocity to the right. So this is position over time. And this tracker was helpful in order to find the actual position and the time of our experiment that was conducted. Now next we have GlowScript, and GlowScript was a code that was able to give us a theoretical values to tell us where should the ball be at this particular time. And this is some introductory code right here. We have the system mass, which is 0.0027, and we have the initial vector velocity, which was calculated before. Now going to the actual calculation right here, the time of the experiment was 1.6 seconds, so that was placed right here. And these three next lines are extremely important. The first is net force is 0 since we're at a constant velocity. Next right here at line 59, this is the velocity update formula. And right here as well, we have the position update formula. Now this program was run, and this was the ball that was theorized. And this is the position versus time graph right here, and this is the velocity versus time graph right here, constant velocity, and this also shows a constant velocity as well with the linear line as well. And these are all the data points. Now these data points were then compared between Tracker and between GlowScript, and these were graphed on the same plot right here, which is shown. The top graph is the actual position, and the bottom line is the expected position. And now the slopes are a little bit off, and this could be due to some experimental errors, such as an even force applied or improper tracking through Tracker. So all in all, this lab demonstrates Newton's second law, which shows that a force is equal to mass times acceleration, as well as Newton's first law, that anything in motion will stay in motion unless acted upon by an external force. The data is roughly linear, but does deviate from the expected data. So now what if the axes were flipped? Instead of our axes being on this side, on the left, what if they're on the right? And what would happen is that the ping pong ball would be shown to moving in the negative x direction and to the left rather than to the right. Now what does this mean? Is it possible to know how many forces are needed to make the net force 0? No, it is not. The data from the experiment show that the net force was not exactly 0, and this is due to human errors while the experiment ran. It would be much easier to track if a machine conducted the experiment.